Transistors are everywhere, in your phone, in your car, in your laptop, and even in your toaster. They are tiny, but they do heavy lifting for all modern technology. It has always been in demand, but in the last years, because of AI, crypto, geopolitics, supply chain challenges, this industry has become under pressure more than ever. In today's episode of the Montrepreneur Podcast, I talk with a former Intel engineer with extremely deep knowledge and experience in the hardware world. We go on a deep dive into the semiconductor industry, its evolution, challenges, and the technologies that are being developing right now.
Who would have thought that high schoolers would be writing code? You know, it would be ridiculous, right? Silicon Valley is called Silicon Valley because it's the home of the semiconductor industry, right? It's named
somehow granted everything, the whole process in the industry.
The industry is facing big challenges in trying to continue to minimize the size of the transistor. And once we'll get to the atom, that's it. We won't be able to build transistors from quartz. That won't happen. A sort of a big political change to bring more and more industry back to the United States, right?
Is there like anything that you're really looking for probably like in the next 4 or 5 years?
With hardware, it doesn't work like that, right? If there's a problem with your design, you'll have to remanufacture it. Yeah, I mean, most people don't know it, but they encounter hardware bugs quite more often than they think, right? Missiles, tanks, airplanes, whatever. Each of them has like hundreds of chips.
The last thing you really need is money, because money is just like a thing, it's a multiplier, you know?
Not to mention the fact that the entire rest of the American economy is really dependent on this industry.
How fast everything is going to change.
I really enjoyed my conversation with him and learned a lot, and I hope you do as well. Welcome to the Montrepreneur Podcast.
Okay, Moshe, I really appreciate you taking the time. I'm very, very glad to have you as a guest on the Montrepreneur Podcast. So welcome. Thanks a lot.
Thank you very much, Mutassan, for having the most important guest. I'm being here and talking to you. I'm always passionate about talking about this technology. So great to be here.
Okay, great. Moshe, I saw your pitch, I think 5 months ago. You were pitching on a startup accelerator, and the only thing I remember after the pitch that I don't understand anything about what you were doing. I knew that you are working in the semiconductor industry. I know in general what is it about in that industry. I know that it's very, very important. Like every cell phone, every electrical device, every anything we use like in our daily basis has something to do with that industry. But I have, even as like a software developer, I really don't have much idea about it. That was like the reason why I invited you, because like, okay, that's very stupid actually from my side. So tell me, what is it about, and what's like the thing that really like, what's the reason why you went that way?
Can you repeat the last question? Why?
I mean, what excited you about that industry to get into it?
Well, I think the thing that excited me most about it is the sort of simplicity of it, and how from that simplicity you can have something incredibly complicated. Because if you look at a chip, at the actual chip structure, it's not all that complicated, right? If you just, for example, compare it to a structure of a very complicated piece of software, right? That could be like billions of lines of code, and with all sorts of really complicated parts in it. But a chip essentially is built from pretty much the same building blocks, which are called transistors. That's the thing that every young engineer starts to learn about. And a transistor is essentially just a faucet. It can be on or off, and that's as simple as can be. And from that, all of the advanced logic that we have on the planet, that is where basically its power comes from. And that's sort of what drew me in, to the complexity out of simplicity. and the fact that there's so much history into this industry, right? I mean, Silicon Valley is called Silicon Valley because it's the home of the semiconductor industry, right? It's named essentially after the first semiconductor companies that were there, which were Intel, of course, but before that, there were companies that sort of even preceded that, but mostly it was Intel at first. And sort of what Intel did, which was creating the first programmable CPUs, that really drove like innovation throughout basically every industry that uses any sort of technology. And one of the most impactful sayings, or that any entrepreneurs ever said, that is something that I sort of carried with me, is Moore's law, right? That basically technology is going to increase, or performance is going to increase in direct proportion to how many transistors you can squeeze into the same size of chip die, right? And that really speaks profoundly about the importance of technology and how much it's sort of connected into the actual engineering, right? You cram more transistors, everything gets better, right? It's so simple and yet so powerful. So that's what drew me into the industry.
Okay, cool. So generally, like, it's the simplicity and how like this simplicity can build very complex, important stuff, right?
Yeah.
Okay, and talking about the Moore's law, I really heard. I don't know much like about the how. I mean, how. What kind of scalability did we arrive like in the last year? But I heard like that it's slowing down. Is that right?
Yeah, that's correct. The industry is facing big challenges in trying to continue to minimize the size of the transistor in order to continue and cram more transistors, because more transistors means more devices, and more devices means more logic, and more logic means more performance. Right? But as we get closer and closer to the size of the atom, as you can expect, there are all sorts of physics phenomena that make things very difficult, like things like leakage currents, that is, current going from one end of the transistor, that is, from one end of the transistor gate to the other side, when there's not supposed to be any. Right? Imagine you're closing a faucet, and despite you're trying to close it, there's still some dripping out. Right? So that dripping out is not so bad when it happens at home. It sort of ramps up your water bill, but other than that, it's not really all that bad. But in transistors, it's absolutely horrible, because when you have that current continuing to drip out, then you don't really know whether that transistor is in 0 or in 1, right? So that makes it more difficult. And there are quantum effects. There are all sorts of things that they're called parasitic capacitance. All these physics phenomena that really makes toggling the transistor from 0 to 1 and back to 0 much more difficult, which is why we're seeing it slow down. But the good thing is that slowing down has sort of spurred companies into exploring all these new technologies to improve performance that don't require reducing transistor size. So that's sort of a blessing in disguise.
Cool. But do we have like any alternative technologies? That's solving this problem, or what are your thoughts about that?
Well, unfortunately, no. There's no way to go around physics and make a transistor smaller than an atom, right? There are things that they're sort of able to push the transistor size closer and closer to the size of the atom, but there's no going around the fact that it will become a greater engineering effort as the closer we'll get there. And once we'll get to the atom, that's it. We won't be able to build transistors from quartz. That won't happen. But there are other avenues of computing that are being taken. Like the most notable one is quantum computing, which has a lot of upside. But there's also silicon photonics, and biological computing that are sort of emerging technologies, not as famous as quantum computing, but they're around as well, and they also have all sorts of interesting applications.
Okay, interesting. Like I really had the feeling in the last few years that I have been hearing these words like much more than before. I think the drive for that probably like was AI, probably some global changes, also like the supply chain, probably, etc. Like a lot of factors that could play a role in that industry. What is, in your opinion, like the biggest driver of that, of the merge of the whole technology?
Well, you touched upon the two biggest things right now, like several emerging technologies, right? Machine learning and specifically generative AI right now is in the forefront of that, but there's also crypto and a bunch of other technologies that require very intense computation in order to get off the ground. And that computation is so intensive that even general purpose computing isn't really cutting it anymore. So there's a lot of chips that are purpose built, not just for machine learning, but for example, for specific stages of the machine learning process. Might be, for example, the teaching steps in which you sort of take data and cram that into your machine learning model so you can learn. So you have a chip that sort of processes that very quickly, and then you have the testing, the part where you test your model. So there are chips that can do that very quickly. Then you combine all these together, and per watt, they are very, very efficient at what they do, and that, especially for NVIDIA, really push the growth of the industry. Like for NVIDIA and for other companies that do that. And the second thing that has kept the semiconductor industry in the news recently is the geopolitical aspect of the industry. Specifically, the fact that a lot of this industry is located in Taiwan, right? Specifically manufacturing, and more specifically TSMC, which is the number one manufacturer of advanced chips. Right now, I mean, as far as I can remember, it manufactures about 75% of all advanced chips in the world. Maybe right now it's a little bit less because there's a lot of investment recently in fab in the US. But yeah, it has tremendous value for the worldwide semiconductor industry. And because Taiwan is constantly being threatened by China, and these threats are sort of becoming more and more tangible as time goes on, this really sent a big fright across the world, or at least in the advanced countries that rely on chips, and especially the United States. The United States has sort of, since World War II, made a point of being very self-reliant. And there's already been, like in the past decade, a sort of a big political change to bring more and more industry back to the United States, right? One of the reasons, or one of the big topics in the last American elections, or in the past couple of American elections, to bring back manufacturing to the U.S., right? Because it all left to the far east, and that really causes problems within the United States. And the most important to them right now is semiconductor, because even things like weapon systems have a lot of chips in them, like missiles, tanks, airplanes, whatever. Each of them has like hundreds of chips. Not to mention the fact that the entire rest of the American economy is really dependent on this industry. So the fact that this was overlooked so far really made the sort of American leadership go into a frenzy to bring as much of this industry back to the U.S., which is also why it's really important to why they put huge incentive for semiconductor companies to go back. But building fabs takes a long time. Right? It take a decade to build a chip factory because the technology is so complicated and you need sort of very sterile conditions, right? Because of it, until the major fabs are built in the U.S., pretty much the entire world is dependent on TSMC. So this topic is going to be on the news as long as as long as Taiwan is threatened, as well as the world chip supply.
Okay, cool. I mean, like you mentioned that also affects the investments that's going to that industry. How hard is it actually to fundraise in this time actually? Because I know that you had a startup in this field. We are going to talk about it in a few. If you would like to share, like, is it about? Because I knew like for a long time it was like a startup under it was like kind of a secret. So if you would like to share, I would be happy to hear. And also, like, how hard is it to fundraise in these times actually?
Well, it's extremely difficult to raise. There are very few funds that actually invest in deep tech in general, and even less that invest in semiconductor. And getting investment in semiconductor in pre-seed or in seed is incredibly difficult because it requires tremendous resources in order to advance. In my case, it's actually a little bit easier because we're a semiconductor EDA company and we're not developing our own chips. But still, it's pretty difficult, right? Which is why there aren't a whole lot of semiconductor startups. Like there are a lot more than that do cyber and crypto and things like that are easier to find. But unfortunately, what companies build is important enough. Sometimes they get help not just from VCs, but from CVC, like support from NVIDIA or Intel or companies like that. That does exist occasionally if they believe that there's a synergy.
Okay, cool. I would love to hear like more about your startup, your story. If you'd like to share, like,
Yeah, sure, I'd love to. So I've always worked in the hardware industry. Past 7 years before I started the company, I worked at Intel. And throughout my time in the industry, I noticed that chip technology is getting more advanced and more complicated. The tools that are invented, the physical tools, what's known in the industry as AT or automatic testing equipment, is also getting better. But the sort of software that comes with it that enables the automation of like machine recipes and DKM, that is best known methods, and all sorts of other things like for example automatic test generations, things like that. That really didn't make any headway at all. Right? There are sort of small solutions along the seams between like the physical testing segment, which I was a part of, and other segments, but things that are sort of classic physical testing, right, or lab testing. There was nothing really there. And after realizing that Intel wasn't going to do anything about it, not because it was sort of uniquely anti-innovation, but because corporations in general are anti-innovation, and because it's just not their core focus or their core competency to develop their own tools. They want to focus on building chips and not in building tools for their chips. Then I realized that this problem isn't going to get solved until I solve it. And so I started my own company, hoping to basically bring the same modern capability that exists in other segments of the semiconductor industry to the specific segment of physical testing, or known in the industry, silicon bring up or post silicon validation, to reduce the massive investment in this segment, to reduce time to market, and to bring all these other benefits in this segment. So that's what we do right now. And of course, it's a massive segment right now. We're focusing on signal discipline. And right now we're still in product development because, like I said, it's a deep tech industry. Semiconductor EDA requires quite a lot of development time.
Sure. I mean, if I understood that correctly, so you really help in the process after, let's say, manufacturing, and when it comes to testing for like specific standards or quality, etc. So you help in that sector, right? Or
right, and specifically, right, if we go over the entire spectrum of the semiconductor industry, right, broadly, from 10,000 feet view, it starts with your basic concept of what you want to do, which includes the the business and technical requirements coming from customers. Then those requirements are translated into a design, right? And of course, I'm speaking from a very broad view because
Yeah.
the design process itself is very, very can be divided into a lot of steps itself. But generally speaking, after the requirement steps or the planning step, you have the design step in which all the control circuitry and code is created. Then it goes into what's known as the pre-silicon validation step. That is testing the chip before there is a chip. How do you do that? With simulation and emulation. You build like a sort of a digital twin of the chip, and then you run all sorts of scenarios on that, and see what works and what doesn't work, and then you can find all sorts of bugs. Unfortunately, simulation in general isn't perfect, right? That's why, for example, car manufacturers do crash tests and do test drives because even a car the simulation is perfect, and a chip is far more complicated than a car. So the simulation is even less accurate. In fact, at least 20% of everything that simulation creates in the semiconductor industry is just garbage. So there's a lot of bugs that fall through that safety net. And so another safety net is required to catch all those bugs, right? So the way it's done is after the pre-silicon validation step, there's another step called small-scale manufacturing, right, in which a couple of thousands or tens of thousands of engineering samples are created. They're sent to post-silicon validation labs, and then those engineering samples are tested from every possible direction. If the tests are show that the chip is okay, the design is okay, then it's sent to mass manufacturing. If not, it's sent back to the design, and we have an iterative process. Right. So all the segments that I've just talked about are, I wouldn't say fully automated, right? They're partially automated, right? You still need massive involvement of engineers, but at least you have all sorts of automation software to increase the productivity of the individual engineer, right? With the only exception being post-silicon validation, right? In this segment, everything is done manual. There are barely any tools to increase the productivity of the engineer. And as a result, when you have higher complexity of chip, that is more device per chip, the only way that you can essentially tackle this rising complexity is to hire more people, buy more tools, buy more infrastructure, and then cost rise along with what they cost rise with time. The best number that illustrates that is the fact that in 2007, only 2% of overall chip cost went to post-silicon validation, and today it's about 20%. So that's a massive rise.
Okay, awesome. Actually, it's very, very interesting for me because, like as I said at the beginning, it's like a buzzword. I know that it's there for me. It's like somehow granted everything, the whole process in the industry. But now when you are telling me about the whole process, like from the requirements to the design to the manufacturing, also like the testing, all makes sense. And to know that also there are a lot of problems, like. Yeah, it's like logical actually, but it's like nothing that I think about you do like on my daily basis. So very, very interesting.
Yeah, and it has serious problems, right? That a software designer sort of wouldn't trouble himself with, because when you have a problem with your software design, you fix your code, you recompile, or if you have it like scripting language, you don't even have to bother with that. And then you try it again. You do a unit test, you try. With hardware, it doesn't work like that, right? If there's a problem with your design, you'll have to remanufacture. So you have to be like on the nose as much as possible in your design. And if you're wrong, it costs you a lot of money in remanufacturing, especially with that technologies. Manufacturing takes a long time and costs a lot of money. Right? So you have to be as sort of correct as possible about what you're doing. And even if you're wrong, you still need to find ways to sort of avoid manufacturing as much as you can by using, for example, using programmable components in places that you know are sort of prone to failure, by using fuses, by using as much sort of creative play with your bias and microcode in order to sort of bypass all sorts of bugs that were found in the design. And a lot of companies manage to do this successfully. All these workarounds in order to avoid remanufacturing. But companies that do really most advanced chips out there, like Intel and Nvidia, they have like for their advanced products, they have like at least one or two remanufacturing cycles every product.
Oh, interesting to know because like I don't know, like usually when you use the software or something, you find some bugs here and there. But I never thought about that. I never had like some bug in with my iPhone, like okay, let me send it back. So that's probably like the reason why, like for people like me, like we think it's just granted, but interesting.
Yeah, I mean, most people don't know it, but they encounter hardware bugs quite more often than they think. For example, if you encountered a blue screen on your PC,
True.
that's a hardware bug, right? People like to blame, oh, this is a damn Microsoft. Like, no, that's Intel or AMD. That's right. Right. I'm defending Microsoft here, and maybe I shouldn't because they're not people's favorites, but actually, that's a hardware problem, right? Like Windows problems, they have like your your standard Air Windows and Windows, but the blue screen, that's a chip problem, right? And sometimes you have it in your phone as well, but that doesn't come with a blue screen. Usually, your phone just automatically like restarts or something, right? So it's more common than you would expect, but also because hardware bugs are so disastrous. A lot more money is spent to make sure they don't happen. Unlike software, that if bugs happen, we'll fix it in the next version. It's not such a big deal.
True. Yeah. Okay. Interesting. So at this point, I would be very interested, like, to hear what are the coolest technologies like you heard about in this field, or what are the like upcoming technologies?
Yeah, there are a couple. Mostly, like we said, is driven by the fact that Moore's law is winding down. Um, the first one I'd say is pretty cool is what's known as power V. The reason why it's cool is because it completely changes how a chip is built. Like if we compare like a chip structure to a cake, for example, it's pretty similar because a chip ultimately is built from layers. Like you have like a bulk silicon layer. You have beneath that you have transistors. Beneath that you have all the wiring that supply both power and the signals to the transistor. Right, that's how all transistors until now were built. All chips until now were built. Right. So that is pretty much like your cake was built layer after layer after layer. The power via technology changes that so that you have basically the transistor layer sandwiched in between wires, right? So you have power wires on one side, signal wires on one side, and then you have your bulk silicon above that, right? So why is that important? It's important because when you have power and signal wires intertwined, it causes several problems. First of all, it means that basically power and signal wires are vying over space, over real estate in the chip, which means a lot of times you have to reroute the power the power wires that they would be longer because they're sort of twisting between signal wires until they reach their final target and reach the transistor, which means longer power wires. That means more waste, right? Means more extreme voltage falling on those wires, meaning eventually, if we look at it from the user's perspective, it means eventually more power consumption. So if those power wires won't have to compete over space, that means that they can be wired much more like in a straight line, sort of, right? Or at least less twisty than they used to be. And then you can basically route them with less distance from the point where they're connected to the board, like to the test board, or to the motherboard, to the eventual transistor that they need to power, right? And that saves quite a lot. That saves, as far as I heard, it saves about 15% of the chip's power, the technology. So instead of I don't know, lasting 10 hours, your PC could last 11 and a half hours, like just from using this technology. But another interesting thing that this technology does is because it separates the power and the signal wires, it means that there's a lot less electronic disruption on the signal wires by the power wires, right? So that means that the signal wires are more stable, there's less interference, which means less errors, which means that they don't have to, the engineers designing these things don't have to have as large of an error margin as they design it for. They can have a smaller margin of error, which means that they can sort of lower the voltage, and they can increase the toggling speed and do all sorts of things that increase performance as well. So for the user, that's an amazing technology. Not so much for post-silicon validation, if you already discussed that, because the transistors are sandwiched in the middle, and there are quite a bit of post-silicon validation discipline that actually require access to the transistors. So that makes their life a lot more difficult. But for the user, it's an amazing technology, saves a lot of power, and has the potential to significantly raise performance. Another interesting technology is sort of a dual technology, right? It's two technologies that do basically the same thing. It's chiplet technology plus advanced packaging. Chiplet technology basically breaks down one die into a lot of smaller dies, right? So one chip to a lot of smaller chips. This technology sort of wasn't initially meant to benefit the consumer. It was meant to benefit the manufacturer. Why? Because if you have like an entire wafer that you need to manufacture, and you have like big chips, like server chips, like that take up a lot of space on the wafer, and because of it, you can only fit like 4 chips on one wafer. That means that if you have like a speck of dust in the manufacturing process land on one of those places where you're supposed to have a chip, then that's one chip that's damaged or destroyed, right? But if you have 100 chips and a speck of dust lands on some place, that's one chip out of 100. So the more chips you can cram into one wafer, right, and divide it into more and more and more chips, that means you can increase what's known as the yield, which is the amount of good chips you have out of the entire wafer, right? So that's why the entire industry is going toward the chiplet technology to increase manufacturing yield. That increases the amount of money that these companies can make, and eventually those savings can get to the consumer as well. But it also has a benefit from the user, and that benefit is if you have more chiplets, right? So for example, if you have a chip today that has like four CPUs and like 2 GPUs and another bunch of like functional areas that do different types of things, then if you divide them and have like a separate CPU chip and a separate GPU chip and a separate like outside interaction chip and an outside memory chip and all these different things, then you can have a lot more different combinations, right? So you can do a lot more custom chips that are, exactly the right chips for the certain type of customer, right? So you will have a huge explosion of different types of product in the industry thanks to this technology. Right? Now, if you have chiplet technology, you have to find somewhere to connect all those chiplets so they can talk to each other. Right? Otherwise, you didn't really do anything here. And that's where advanced packaging comes in. Advanced packaging is basically a package that has all sorts of very advanced interconnects that can connect these chiplets horizontally or stack them on top of each other in a way that you don't lose much performance because of those connections. And that eventually what turns all these different chiplets into a single, what the user can perceive as one chip. And in fact, it's a lot of chips under the hood, right? But the user perceives it as one chip, thanks to the fact that it's all incorporated into one package, right? So those are the big technologies right now. Also, there's another really interesting technology called gate-all-around, right? And that also changes the structure of the transistor, right? Which is pretty revolutionary because in like the past 3 decades, the transistor's structure was changed only once until now. This is the second time, right? The first of all, you had like a flat transistor, which in which you had like either NPN or PNP transistor. That's like the name of the different doping types of the transistor, like whether
I heard that somewhere, yeah.
yeah. So it's basically you either had like a flat you either had like a flat NPN or a flat PNP transistor, which are complementary. That's where CMOS technology came from. And it was really simple, right? You had like one type of silicone, then another type of silicone sandwich in between, then a gate and a metal that basically huddles everything, right? Or tells the transistor what voltage it's supposed to be in. It's supposed to be in 1 or 0. So then you have a technology called 3D transistor, in which the middle part, right, the channel, the sort of the other silicone that was sandwiched between the two, like the end silicone sandwiched between P silicone. So that end silicone went into the channel, and the channel surrounded that bit of silicone. And the reason for that is because then you have more active area for the gate to use basically electrical force to draw charges and connect the channel, and that meant higher switching speed, right? So that was the technology that came out, like if I'm not mistaken, in the early 2000s. And then now you have the gate-all-around technology, in which you're surrounding the gate area all around with the channel area all around with a gate. So you have maximum electrical impact over those channel areas, so you can draw and repel charges as quickly as possible, and that's supposed to increase toggling speed even more. Right, so you can expect in the next like 4 or 5 years, when the technology really picks up, that you will see an improvement in clock speed. Right?
Yeah,
So
it's very, very interesting. Like the only question I have in mind, like about all these technologies you just mentioned, like, is it just on paper, or do we have them also in practice right now?
Well, right now it's pretty much on paper. There are a couple of sort of edge products that are sort of at least a couple of these technologies are applied to. Like gate-all-around right now isn't ready, but some of these other products like chiplet technology and advanced packaging, you can see sort of a trickling of these products into the market. But these are mostly edge products. They're still not, for example, NVIDIA's flagship product, right? The GPU that you have in your PC, right? Because those products are still not there in terms of reliability. The companies still don't put the technology enough. But as they become more mature, you will see them all over.
Okay, interesting. I mean, I would be really wondering like how fast that will happen, and when that happen, like how fast everything is going to change. Because right now AI is, I mean, like, I don't know, in the last 10 years we heard like, okay, it's coming, this technology, and right now, like, it's really, I mean, I cannot imagine my life without AI right now, like on a daily basis, and everything is moving like very, very fast. But how would you say like that will change our daily life when these technologies are really embedded and implemented?
Yeah, I think it will have a tremendous impact, because I mean, I don't think in terms of computation, all these technologies will increase computation speed by 100. Like, it won't have that dramatic impact. But even an increase like over the next 10 years, like 3 or 4 times in terms of computation speed per watt, makes a big impact, because it means that your average user would have much more access to all sorts of AI products, right? Because a lot of the AI products are so computationally intensive that you're sort of the cost of computation is enormous, right? To the point where your average user wouldn't be able to afford it. Like, just imagine if you're an AI company, and you're basically your cloud usage, your cloud computing usage per, let's say, one solution,
Mhm.
right? $10,000, right? So you would price your product at $100,000. So obviously, it would be an enterprise product.
Makes sense, yeah.
Person wouldn't be able to use it. But if you make it a lot more energy efficient, even let's say, even for the same amount of performance, then suddenly it becomes available to your average user, and that could make a big difference. Just if I could compare it to a different technology, it would undergo the same process that 3D printing went through. Right? If you remember, like 40 years ago, 3D printing existed, but it was confined to basically to enterprise, right? Because it was not really mature. You had to have enormous resources to be able to 3D print. But now, people, buy it off of Amazon, like a $300 3D printer, and you could buy a good one with $300, right? And put it in your PC and on your desk, and it's incredibly accurate, right? So I think that as computing becomes cheaper and more efficient, it doesn't even have to be drastic, right? It can be like several, like even one order of magnitude. It will make a big difference because it will bring technology from the enterprise level to the individual user.
Okay, awesome. It's very, very interesting, like especially the energy thing, because like as you say, like AI is going to need a lot of energy, and a lot of people thinking about that concern, that how can we afford that? I heard that, I don't know, like which company, I think Microsoft or something, was financing like a nuclear let's say, I don't know what the name of that was, like yes, the power place. It's just to be to be able like to afford that in the future. But if we like really optimize on that low level, that's awesome.
Yeah, but that means that, right, in order for companies to be able to offer you services that you sort of don't have on your desk, they would have to build even more energy intensive applications, and so it will never end this way. So you will always have need for more energy, right? At least until we get to sort of biological computing. Right now is very far away, but if we get to that, that's supposed to be a very low intensity application of computing.
Okay, nice. I'm thinking right now. Sorry, because just my camera went out, but it's okay. I mean, we have the recording here. Yeah, sorry, we don't have enough energy for the camera. I mean, the battery is just can only record 1 hour. No, if I am like completely new to the industry, I mean, how can I put my feet into the door, like of the semiconductor industry?
Yeah, I mean, my recommendation is go through the software stage, right? Because the biggest semiconductor companies in the world, most people don't know, but they're also the biggest software companies in the world, because they have to develop microcode and BIOS and all sorts of drivers, so things will be compatible with their chips. And they also develop a lot of open source code, so that would have an impact on open source. So, for example, like Intel right now is not in a good state. It fired a lot of people, but when I was there, like out of the about 120,000 people working for Intel, about 10,000 of them were software engineers, right? And within those software engineer group, you have like QA, right? Just like in software companies. So that would be a really good place to land, right? And from there, sort of advance, learn the industry, go down from QA to sort of software engineer, and then sort of work your way down towards sort of the metal layers. And what do I mean by that? You can build sort of very high level code, like I don't know, like a software that helps you update your drivers. And actually, Intel has that software that you can download that helps keep your drivers updated. And then you can go a little bit closer to the iron and or the copper, should I say, and develop the drivers, and then go a little bit deeper and develop the BIOS, and they go even a little bit deeper than that, develop the microcode. And if you want to go even deeper, then you can. By that point, you're pretty sufficient in hardware. If you develop code that's sort of that close to the actual structural foundation of the chip.
Interesting. Okay, and like you're saying, just enter the industry from the software perspective. Try to go high level as much as you can. Try to be the tester or whatever, like to understand the other parts of that, and then like go a little bit deeper. Try to write code like to for drivers, for example, like, and then go deeper and deeper. Interesting. Okay, but like what kind of other backgrounds? Sorry.
And so on. Of course, if you just study electronics engineering in university, then you have sort of the fast way into the industry, of course.
Yeah, that was actually like the second question. Like, what kind of thing do you usually study for that? Okay.
Yeah.
Okay.
Electronics engineering, also there's a lot of demand for like physicists, mathematicians, algorithms, like there's a lot of different professions working that this industry required, like chemists for manufacturing, process engineers, a lot of things.
Interesting. Okay, then my second question would be like, and like you were an expert like in that subject when you started to go to the entrepreneurial way and just start to make something in the field. What was like the biggest the challenges you got, and now like after around 2 years of being there, what would you make different if you are doing this decision right now, for example, with the knowledge of today?
Well, the knowledge I have of being a founder, especially in terms of fundraising, I wouldn't even go to fundraising route. I would look for as many complementary co-founders as I can find, and just tell them, here's a bunch of stocks, come work for free, because the biggest cost you have is manpower, and then you have essentially almost unlimited runway. Like there's a little bit money that you have to pay for lawyers and for accounting and whatever, right? But even that you can really postpone. You don't even have to build a company until you have sort of your initial traction. And at first I thought that your company wouldn't even take you seriously if you don't have a company. That's not true, right? Even if you're an engineer, a knowledgeable engineer, you can approach people through LinkedIn, and some of them won't get back to you, but a lot of them will. And if you're knowledgeable and you show that you can bring value to their company, they'll bring it. They'll start bringing that up the food chain, and you can really promote things, and you can sort of spend your first serious dollars right before you sign contract, right, or very least start PLC, and that really saves a lot of money. That means that you don't have to fundraise. And I'll tell you right now that my next company, that's exactly what I'm going to do.
Okay, cool. No, I totally understand. I mean, I also did the first failure with I did the same failure with my first startup. I was like really, and I mean, my understanding about successful startup was okay if we fundraise, but then when I really understood like how fundraising works and etc., the last thing you really need is money, because money is just like a thing. It's a multiplier, you know. If you're doing great, even on a smaller scale, you just take that money and just make it scale. But if you don't arrive like that sweet point, there's really no point of that. You don't need that money.
Yeah, and you know that there's plenty of companies that even don't need that to scale. They just grow organically, right?
Yeah.
Yeah, and not just that, but the amount of effort that founders put into fundraising is just unbelievable. Like there are times where 90% of everything I did was just fundraising, right? I talked to, I think upwards of 600 investors during my time in the company, and that's like right. That's way too much time spent on that, but that's how I built the company. So I didn't really have much of a choice there. But yeah, but that being said, there are sort of exceptions to this. If you are like in a trendy field, like if you're cybersecurity and you have like companies jumping all over you just to give you money, there are examples of that happening. Not too many of them, but it happens. Then it would be wise to take the money. Not necessarily because you actually need it, but because if you don't take it, they'll just give it to your competitor. Right?
Yeah.
So in that case, it's just good to take the money. So those VPs that invest in you will get out of the system. Okay, we invested in this specific type of cyber security company, so there's no point in also investing in your competitor, right? And also it will be a conflict of interest. So that's how I see raising everything to do with fundraising.
Yeah, interesting point for sure. Okay. What do you see like the future vision of the industry? You told me like about the whole technologies, etc. But is there like anything that you're really looking for, probably like in the next 4 or 5 years?
Well, something that I'm really looking forward is sort of democratization of chip development. I mean, if you were to look at like the software industry in the 80s, right? Who would have thought that high schoolers would be writing code? It would be ridiculous, right? Everyone knew that just corporations write code in like B language or something before the C was invented, or even with with the ticketing and the punch and hole into tickets. Like it was ridiculous, but there are all there over time came all sort of software, like higher level software, like programming languages, and all sorts of software that made it just a lot easier to the point where even like primary school students program these days, right? At least simple things, right? But the chip industry, that didn't really happen. It's still sort of reserved for industry experts, and that's really something I'm looking forward to the point where you can have just your everyday person basically designing their own chips, sending that to a fab, and then getting back their own chips, doing their own thing, like for a school project or something like that. I think that would be really cool. And actually, Israel Lab, technically speaking, is developing an EDA system that not only makes life easier for enterprise, but essentially it also would make life easier for your end user that could do that, essentially develop chips on their own.
This is actually a very interesting like view to see the things. I never thought about it either. Like just designing things at home, sending them, and having like your chips in your drawer or whatever. It's actually very, very cool. Yeah.
Yeah, man. Then you can. That will also usher I think a new stage of entrepreneurship and innovation, because you
Sure.
don't really need to depend on sort of an outside supply chain. You can build your own chip, your own software. You can print your own like physical mechanics that interact with your product. So you can basically build everything from scratch, like in your home garage, right? So that could really help in everything to do with entrepreneurship.
Good, awesome, and I really, really appreciate it. From my side, I don't have like any more questions. If you feel like sharing something or any interesting thing you want to share, so it's your stage right now.
Well, an interesting thing that we're doing right now, right, and I'll stop with that, is we're automating a discipline called circuit edit, right? And circuit edit is a fascinating discipline. I think it's out of all the sort of discipline that exists in the post-silicon validation segment, I think this is the most fascinating, because it essentially relies on particle accelerators known as bit tools to accelerate ions and basically hit an engineering sample, hit that sample, sort of drill like in a nanometer scale inside a chip, and then change its internal wiring and thus change its logic, right? And that's just the coolest thing ever, right? To basically redesign physical chips, right? Not in software, but in rewire physical chips using particle accelerators. I can't think of anything cooler than that. And right now, we're basically developing software that enables the automation of that process. So I thought that was a cool fact to share.
I think it's like cool enough that I have to make some research after the episode. So that's good. I changed my mind. I do have one question. Quantum computing. What are your words on that?
I think it's very promising technology. It can do a lot of really amazing things, but it requires some big breakthroughs in sort of basic science in order to really get off the ground. As far as I heard, like Microsoft had a big breakthrough recently. But the biggest problem there is the cooling issue, right? In order to make quantum computing work, you have to really cool down the qubits into almost absolute zero. So actually, sort of the cooling apparatus takes the most space and the most energy out of everything else in a quantum chip. So once you can reduce those requirements, you can really cram in qubits and then start to really add the advanced logic that you have in normal chips, right?
Okay. The reason I was asking is actually like to figure out like what do you think about the next hype, because I mean like 10 years ago, we had all of us heard about AI, but it was not that hype. It was like boring. Okay, yeah, it's like far away. And then like everything is changing. Like all investors are investing in AI companies. If you don't implement AI, so you're like are on a disadvantage, etc. And now like AI is the hype. So what do you think is the next hype? Because all the technologies you are just mentioning, for me, are bringing us like steps further.
You mean how? Can you just repeat the question? Like how?
The question is like from all the technology you just mentioned, like what do you think is the next hype? Because AI, we have this hype right now. I mean, but all the technologies you just mentioned kind of give us capabilities that we don't have at this moment if they really like get into the practice. So what do you think, like from your expertise, is the next hype to invest in, like in a few years?
The next hype. Well, that's a tough one. I think that the next hype will be silicon photonics, because essentially there will eventually we will run out of ways to make chips more energy efficient, and the best way forward to make chips even more energy efficient is to go with sort of light computing. Like that is, you will essentially use the same mechanisms that exist in fiber optics in order to sort of simulate what transistors do now. Right? There's also already sort of limited efforts to go there, but I think it will pick up steam once people understand that the traditional technologies are going to get stuck eventually. So we've got to avoid that and walk into new directions. And I think out of all the technology or emerging technologies right now, silicon photonics requires the least amount of basic research in order to move to the center stage. So that would be the new technology or the new thing that everyone would invest in to replace traditional computing.
Yeah, interesting. Thanks a lot. Then this time is really like I don't have any questions anymore. If you, if you'd like to share, like where people can reach out to you, with all the interesting knowledge. So
yeah, sure. People can reach me at motion.noi@caesarialab.com. We can also through our website we have a contact form, caesarialab.com. And you can ask any question for a partnership or for just learning more about the company, and I would love to answer.
okay, great, awesome. I will share that in the description. Then Moshe, I really appreciate like you taking the time, all the knowledge you just shared, and I wish you all the best with your startup. Thanks a lot for being one of the best guests on the Montrepreneur Podcast.
Thank you very much and good luck.
Okay, great.